T2 demos. T2 demos. T2 demos. This is the first test to try to do time-lapse with the X-T4. There's the parameters. We're going 300 times. Speed up, these are JPEG frames. There's lots of problems with this, but it's fairly encouraging. I'm worried, since this is just one power zone, I'm worried about when we get to like 9 power zones, whether there's going to be enough res. But we'll see in the second demo where I do some camera projector automation, I'm calling it, that it looks pretty good. We can push from here, we can push all the way into a single tile after the fact and still like read the text, for example, which was not really true with the previous solutions. I don't know if that will still be true with 9 power zones, but we'll see. So this was a big update of almost everything, because I hadn't had this grid fired up for quite some time. I'd been working on the single ring, and then obviously just doing a Hugene run, which I wanted to run until it settled one way or the other all by itself, but I didn't really understand how the Fuji X-T4 works, and its battery died. So that's where this simulation ends. All right, so here we are pushed into a single video, also with a little bit of color grading, since the background of the CDM menus really should be brown. And the LCDs we're using are really so low quality. So I've just tried to get this to approximate, to sort of emphasize rendering what passes for true colors on the LCDs, and let the the T2 tile cases and the surrounding environment and stuff go hang. But I'm also, and this is using the Kdenlive transform effect with keyframes that are set to smooth, which is cubic splines, I think, and I'm starting to get them working. You can see that this is actually fairly smooth, and it doesn't have a lot of changing in directions that don't make a certain amount of sense given the action on the screen. So this is it. This is the first test. I've now got an order for one of these dummy battery things that connects to a charger so that it's not relying on USB power. So hopefully we'll be able to do much longer. Lots more stuff to do. Just figured I'd put the first test up. That's it. set. Hey folks, welcome to the Artificial Life Advanced class. It's T-4 in the Artificial Life Creation Countdown. Here is the master spreadsheet. We are way behind, but I haven't given up. There's a Slack built into the system, the stretch goal, we can dump that. There's the entire month of November that's not booked. We'll see how it goes. So the goals for this time, Diamond Sequencer, that's the sequential machine that we're trying to make that'll control the whole reproduction process. It's supposed to have programs running, not even close. Spike Assembler and Loader, a prototype of something that's going to actually take the program code that's going to exist and put it in and get it deployed onto a Diamond. Made some progress on that. Take a look in the simulator. So just going to try to set this up, get it going, and some color commentary. All right, so first it's going to spread out. There it is. We have our Diamond Sequencer. This is our loader. This is the new thing here. One of the aspects of the loader that we have to deal with is that as it injects instructions, it has to be careful not to use up the last empty space. Let's see this first bit get as far as, all right, so there we are. Okay, boom, and now we're cooking. So the loader is now down here, and that's our primary aggravation bug at the moment, is that the loader doesn't stay in place, and it's the worst excuse for deterministic serial computation that one is likely to encounter today. But we have deployed a marker that has its special label that is in honor of me for having gotten this far. And we've also deployed a Zong just to take up some space. The program that we're doing here, have we got the program, is this. So there is our marker. And it gets sucked into the label here as part of the first instruction. Here's a zong, another zong, and then finally we're going to put in a reset instruction. So far we have a marker and one zong. All right, now we got a shapeshifter. It needs to find available space. Oh, it all happened. It all happened already. That was just about the first time that I got this working this far. And you can see this white one here and this black one here. Those are loop killers. They're actually part of the execution of the reset instruction. So things started to happen. I'll come back to that a little later. All right. The bugs that that thing is full of are not just because I'm old and forgetful and not as good a programmer as I used to be. They also reflect a fundamental tension between trying to keep total control of everything and trying to just be all completely loosey-goosey. And, on the one hand, we normally think of control versus chaos as being like a binary distinction. So traditional computing, deterministic computing, is top-down, rigid control. Nobody can do anything except when they're told to, and then they must do it. Authoritarian social societies try to do the same thing, and it never works. Of course, the problem is that top-down control in like deterministic computers works for small systems. So people think they build a small system and say, hey, it works. But the whole point is top-down control doesn't scale up. On the other hand, people think that if you don't keep everybody completely in line, that if you let them have any freedom at all, you'll have chaos, you'll have anarchy, turbulence. But what we're looking for is the space in between where we have resilient systems that consist of robust agents that can survive on their own. And then bottom up, they can make cooperatives to do things bigger than they could do on themselves. And so part of the essence of that is having this idea of slip joints, that things can interact without being rigidly connected. So one can slip and the other one won't go. And hopefully our diamond sequencer will partake of some of this resilience. We shall see. So, the control aspect of diamond sequencer, so here it is. It's a modified form of the HG3 grid, and it's got these 4 pockets around it, and the access to these 4 pockets that represents input, output, temporary space, and the instruction stream. There's a lot of rules that you have to follow about going in and out of these pockets in order to get this reliable sequential stepping that we're trying to produce. On the other hand, the pocket chains that are the things that are going to go in there, and like one of the rules is you can only have one codon, one of these pocket chains in there at a time. They are loosely coupled to their neighbors. Like this EC here, it's not even lined up with the EC that is the next link in the chain, because they don't have to be. They just have to point at the next pocket, and the pocket then points back at them. And hopefully, when we have some gigantic mess like this, though you can barely find the diamond sequencer buried in the middle of it, that will be able to have this combination of control and quietness and reliability in the diamond sequence pockets, the diamond sequencer pockets, the DSPs, while allowing whatever happens out further in the grid, out further in the diamond. We'll see how it goes. To recap the actual grid, we just saw the simulator. On the grid, a couple of weeks ago, we had a crash storm. The underlying Linux stuff got messed up, and it took the whole thing down. Looking at it, there was a hypothesis that possibly in some extreme cases, it might have run out of room in the Linux kernel buffers. So we said, let's up them by 400%, make them 4 times bigger, and start it up again. And that's been running now for several weeks, and it hasn't happened again. That proves nothing, but it's a little bit encouraging. And the question was, how is it going to end? I mean, how is a run on the grid going to end? Is it going to be another crash storm? Is it going to be a power outage? If I lose power to the house for half an hour or so, the UPS is going to die and the grid is gone. There's no backup for this. This is live computation that's happening. It's not even clear what backing it up would mean. Or the third possibility is that I will step in and end it, and that's what happened. I ended the previous run with no failures outside, and now it's running the spike loader, so let's just take a look at it for a minute. So that's just getting started. I'll run it for several more days anyway, unless the code improves enough that I want to bump it off. Yes, I'm not going to recap all the previous T2 project worries, but I figure if there's new worries, I need to report them. There's some kind of issue with the camera and the USB connection to the laptop that's recording the grid. This is a Minolta TX4 that is recording all of this stuff, and it flaked out. And it flaked out when I was away from the grid, and it lost 5 days of data. Now, it was just, let's play guess which diamond grid is going to pop next, so it's okay that we lost it. But even after I got back and I unplugged the thing and plugged it in again, it happened again. I had to power cycle the Fuji completely and mess around with it. So now I'm scared, now I'm anxious that something's going to happen, and when we actually matter, like, the grandchild of the ancestor is about to be born. We shall see. All right, I want to take a couple of minutes just before, I'm not going to go long, to talk a little bit more about sequential computing. And so, last time I was showing this picture from Wikipedia, I called it a traditional processor. Really should call it a sequential processor, because that's absolutely the key to it. Yes, it computes a function. It takes some input, it produces some output, but the real key to it is this circular connection between the registers that go down to the combinational logic, the thing that actually can, make nonlinear functions and add things and do whatever, and then writes it back into the registers, erasing what used to be there. That's the key, so that on the next step, we can bring in all the power of the combinational logic to apply to the next step. And yes, we take some input, and whenever we take it, we produce some output whenever we produce it. But that key of using the same piece of hardware over and over again on each of multiple steps is the absolute key to the power and the risk of sequential processing. Now, I'm not going to take a lot of time on this, but these large language models that have these millions and billions of parameters, that they're fundamentally, by their nature, they're essentially combinational. Mostly, they just sort of feed forward. It depends on the exact model, but you can make them into sequential by taking their own output and feeding it back in as more input, and people do that routinely. And somebody found out that adding the phrase "let's think step by step" made the pre-trained language model, it wasn't trained for this particular task at all, go from a clear fail to a solid C+ on some of these models. And my interpretation is the reason it does that is because it encourages the network to expect to do multiple passes through the whole thing. Well, first I need to do this, and the answer is blah, and then I need to do this, and the answer is blah, rather than trying to just intuit the answer in one pass through. And that is the key right there. That's the sequential computing, again, power and risk. And the risk is okay, what happens if you lose your place? If you just have a feed-forward network, if you just have combinational logic, it's inherently self-stabilizing. As soon as the inputs stop changing, well, then the stuff next to it stops changing, and the stuff next to it flows through until the output stops changing, and that's the answer that you want. Sequential logic cannot do that because it erased its intermediate results. So when you have a sequential computer, somewhere in it, you have to build a reset button. And so that's our title card for this time. You look at all the devices you have in your life. Some of them have a reset button, some of them don't. That's the hallmark of the sequential machine. Reset. What's it doing? It's saying forget all the steps and go back to something where it considers a step one, where now, as long as we can do all these steps again, we'll get the answer that we had in mind. The diamond sequencer is a sequential computer, so we need the equivalent of a reset instruction for that as well. So that was the LX reset. LX, I'm saying, is a loop executable. I'm kind of using it to put at the front of my instructions. And I was working on the LX reset as much as I was working on the loader in the last period. And there's a big question, a design question. You can't reset the entire universe because the universe is indefinitely scalable. And, so in the end, I decided that what reset means is flush the output loop and flush the temporary loop and leave the input loop alone, because presumably somebody else put something useful there. And then once the loops are gone, output and reg, reseed them to a new one, and then move on to the next instruction. So we really don't have time to look at it. We can look. I got a demo. Well, what the hell? We'll try to do it really quick. We do not have enough time, but I'm just going to do it anyway. So here it is. Here's the reset instruction, and I'm just going to give it an event. Oh, and it didn't work. Okay. Well, I guess we won't do it. We'll do it during the live stream. All right. So that is it. The next update is going to be T-3. My primary goal is to have some kind of program loading and running that copies itself. And, that's a big chunk of the missing hunk of the project that we're trying to get to. So we'll see if we can get that far. But hopefully, I feel like we're getting close. And we shall see how it goes. Have some fun as always. And again, after the next update, there's going to be a pre-programmed hold in the countdown because the month of November is booked out. Have other stuff to happen. No updates in November. And then we'll be back in December for T-210. And hopefully we'll have grandchildren for the ancestor on January 3rd. Thank you so much for coming and taking a look. I hope to see you next time. All righty. Hopefully I came in under the wire there. Folks, look at all these folks. I'm going to start up the render as usual, and then I'll be back. If anybody's still around, we can chit-chat and try to get the reset instruction to work. Okay, let's go back to the waiting room for now. Alrighty. What's going on? It wasn't getting enough data. That's weird. We'll see. We'll see if that means anything or not somehow. I don't know what that means. YouTube is not receiving enough video to maintain smooth streaming, as such viewers will experience buffering. Don't know what that means. Okay, Ben, comments. Interesting to see language models improve so much. Yeah, absolutely. And you know, and I really think it is sort of fundamental to that idea that if you have an extremely powerful combinational logic, you know, dozens of billions of parameters or whatever of potential nonlinearities that have been trained up, you can try to do something in one step. You can try to just guess it, but if you can convince yourself that you don't have to, so that you can do intermediate steps, it makes a ton of sense. And it's going to be fragile in exactly the same way that any computational process is. You know, if in the process of feeding back the discussion of the previous steps, you know, if that stuff gets corrupted or whatever, then the thing is obviously going to fall off the line because it's got nothing else except for the state that's being carried through back forward. Diffusion models, on the other hand, look more like robust computing. Yeah. You know, one of the things that was funny when I was learning about supercomputing stuff, an awful lot of the supercomputing applications that people actually run are mathematical relaxations, you know, giant sets of PDEs or whatever that are, you know, simulating whatever they're simulating. You know, they have these non-classified demo programs that people can work on, and then they take it behind the fence, and you don't know what they're actually using the supercomputer for. But you know, the inside's dope. The little secret was that the biggest supercomputers, or this is several years ago now, several generations ago, they couldn't get the same answer twice. If you actually cared about the exact value, the exact floating point value of whatever it was, you know, it didn't come out the same if you ran the program twice, even though it was supposed to be a deterministic program. But since they were relaxation networks that were just sort of falling into a big old attractor anyway, at least that's the hope, you know, they just run the iteration a few more times to kind of wash out the problems. And that has a lot more of the feel of the diffusion models like that, you know, you it's pretty easy to imagine adding noise to something. You know, it doesn't take a lot of brains to add noise to something, and then you train yourself to do the opposite so that you can go from fuzzier and fuzzier and fuzzier, and you just make stuff up. You make stuff up according to what you've seen. It's incredible how fast the progress is happening now. So yeah, absolutely. All right. So I'm expecting that, you know, at any moment, you know, the fans are going to the CPU fans, not the super fans, are gonna start coming on here because the room is warming up. But so be it. Let's see if I can't get that. Is that still here? Okay. So what we had here is, so here's the reset instruction. It is in the pocket of the diamond sequencer. If we look at the guts of the diamond sequencer, the quadrant P status array, that's the proc status, is 0000. That means everything is ready to go. And you can actually tell that because each of the green, blue, red, white diamonds, they don't have a border around them. When they have a border around them, that means there's some operation that's in progress on that quadrant. But now there's no border, and that means everything is ready to go. So theoretically, what ought to happen is, oh, I know what it was. Oh, that was so silly. It's educational point though. So I used the wand to give an event, and I gave an event to the reset, and that was my mistake, because the way Diamond Sequencer actually works, the instructions only get executed by the Diamond Sequencer itself. So this codon here, this RS codon, which is providing whatever information it is, uh, um, uh, not really very much actually, nothing really very important. It is now passive once it's in the instruction execution pocket. But if I now give an event over here on the Diamond Sequencer, if I am not nuts, then we will see the first part of the reset instruction execute. Let's do it. And there it is. Dull. So why is it that I made the Diamond Sequencer be the one that executes the instructions instead of the instruction itself, which seems the more obvious thing to do? The reason is because of geometry, that only the Diamond Sequencer is sitting right in the middle where it can see all four pockets. And if we had this guy executing, if the event window was based down here, it would be unable to get to almost all of the diagonally opposite pocket, DSP, which in this case, it doesn't have to be always, but in this case, it's an input stream, which is an important thing to see. So the Diamond Sequencer sitting right in the middle of all four pockets is the one that has to execute the instructions, because it is when the event happens there, it's the one that has access to all four pockets and can provide that and whatever it is. So what happened is we gave it to the Diamond Sequencer. It did all of its checks. It's a ton of stuff to figure out that yes, indeed, it's time to do an instruction, and then it called a method on the reset. It called a perform method, and it gave it this struct saying, here's the input stream, here's the output stream, here's the register stream. Just use it out of these structs I'm giving you. You don't actually have to look and figure out where they are. I've done that because I'm the Diamond Sequencer. Just do whatever your logic is. And in the case of the reset, LX reset, the first step of its logic is, like I said, to kill the output loop and kill the register loop. And the way it does that is by putting out an LK, a loop killer that we actually saw last time. It's just going to sit there and send another loop killer all the way around the loop the other way. So we can let that happen. That should be pretty reasonable. Right, so there it is. And the one that's sitting there blinks black and white when it has events, just so that we can see what's going on. And now up here in the top, the loop is half killed. It down here, I can't really see how far we've gotten. Go a little further. Oh, there we go. Okay, so now the register loop has been killed. The output loop has been almost killed. And we would like to then have the reset go on to second part of its instruction, which is to seed nice fresh loops in register and output. But, oops, the reset instruction is no longer in the instruction pocket, because that's one of the bugs that we've got to deal with. So we'll let this go. And all right, there it is. Now, just because everything continues to rattle around, Zong, eventually, oh, yeah, all right. So, wow, that was really quick. So I missed it. It happened so quick, but somewhere in there, the reset came through and got its second piece, and it went ahead and seeded a new loop, and then it came around again, and now it's killing it. So, yeah, actually, one of my concerns about the code that's running on the T2 grid now, what I was hoping for was that this code would be able to, at the very least, kind of grow sort of blobby, floppy output and register loops, because I have it seeding them with demos, and the demo loops, they don't use the self-contained growth. They'll go ahead and fill their quadrant if they can. And so I was hoping that we'd be able to see these loop, conglomerations coming out and then getting all collapsed as the reset came around, and then they'd grow again. But it seems like the way the statistics work out on this sort of thing, yeah, you can see it right here. We've already flipped out the seeded new loops and then killed them again. So here we've seeded them and killed one of them already. So I'm afraid that the stuff that's running on the grid won't be very fun to look at, because it won't have much behavior that is actually visually striking. But we'll see what happens. Anyway, so okay, so at least I have convinced myself that it was operator error is why the demo didn't work in the normal spirit of things. And all right, so can hang around for a few more minutes, I guess. One of the things that I realize is when the render finishes and I actually start uploading it while I'm still streaming, that actually fights with the upload, obviously. So it slows down the upload, but whatever. How's the? We still got 20 minutes on the render. So, anything else that I wanted to say? Well, I had a bunch of stuff that I wanted to say, but then I actually, in the process of convincing myself, how to get it down to 15 minutes. I throw out all this stuff and then it leaves my brain. Yeah, and I did, think about how biological systems, like ribosomes and so forth, when they're doing their interpretation of the information produced from the DNA via various intermediate vectors, they do have mutations, but it's place and whipping around, and that feels to me a lot like what I'm trying to get to work with the diamond sequencer. The real problem with it is, unfortunately, can't really tell in this picture. The problem is not the guys in the pockets, but the guys that they're connected to. So, for example, this little guy that we can just barely see the top of him, that's connected to this EC, which is an empty codon, an available codon that we can write stuff into, in the output pocket. This guy down here, he can see the EC, but he has no way to see the diamond sequencer, so he can't tell easily that this empty codon is not movable, because he doesn't know that it's in the diamond sequencer. And out in the world, out just in the loop of the chain, out in this mess, the elements of the pocket chain have to be dealing with all this stuff on their own. They have to be moving around and growing and sending upstream stuff that wants to go upstream and downstream stuff that wants to go downstream. So it's not like they can just do nothing. But the problem is how do they tell the difference between just seeing an empty codon that they can feel free to mess with, because it's just a temp, in effect. That's what empty codons are for. They're just looseness that can be filled with other things that aren't empty to take care of business. It looks just like it was out in the world. Empty codon next to empty codon, I'm going to swap or whatever. So I'm actually going to have to burn another, well, I don't know if I'm going to have to, but I actually am going to burn another bit in the bit budget of all these pocket chains to announce that I've been nailed down because I'm in the pocket. So in the process of entering a pocket, the thing that is coming in will know, because it'll be able to see the diamond sequencer. So it's going to set its nailed down bit, and then the other links in the chain, which can't see the diamond sequencer, will have to respect the nail down bit, the I have arrived bit, whatever it is. So I started to build that infrastructure, but it's not implemented yet. That's why these things are all rolling around. All right. So I guess that's it. I guess we're actually getting into fall here. And I'm surprised that the CPU isn't making horrible fan noise. Now it'll do it to me. Because it is. All right. Well, so I think we're sort of quieting down here. Again, folks, thanks so much for stopping in. Actually coming at a specific date and a specific time, that's a big deal. So appreciate it much. It really helps me say, let's do it. Let's have energy. Like teaching, like teaching in the classroom. But I'm going to let it go and maybe go see about have some lunch, and we'll see what's what. So, okay, I'm going to stop the stream and hope to see y'all in 2 weeks, or, hope to see you in the Discord. Thank you, Ben. Thanks so much for making the time to come live. I'll see you on the Discord.